Andrew, can you hear me?
Yes, Mwalimu.
You are there?
Yes.
Okay. We need more people, mobile people. Duncan? Duncan? Are you there? David? Wendot? Those who are not responding, I will remove them before we start.
Morning.
David? Deborah?
Morning.
Morning.
Yes, Mwalimu Nico.
Okay, good. Humphrey? Are you there? Humphrey is nowhere. Ian Mugambi? Ian?
Present.
Okay. James Muritu? James? Jessica Mwangi? Okay. Julius Omari?
Present, sir.
Kirui Aaron? Wendwa? Use two names. Those who are using just one name, I will remove them. Use two names. Sam Mwanzia?
Yes, present.
Okay. Sylvester?
Present.
Sylvia?
Present.
Okay, good. So let me straight away share my file with you so that we proceed from where we stopped. Where is Dennis? Dennis, are you there? I can't see the class reps. Esther and Dennis. Are they there? Esther? We met last time and the other time, and we looked at the concepts of distributed systems. And I think we stopped at, where did we stop? Andrew? Andrew? Anybody? Deborah? You were there last time? I'm waiting. Who is with me? Anyone with me? Where did we stop? Somebody? Hey, you guys, am I alone? Am I alone?
No.
Yes, Sylvia, please. Sylvia.
Okay, the only thing I can remember roughly, we checked on two extremes of a spectrum of a distributed operating system.
Yes, the tightly coupled and the loosely coupled.
Yeah, the loosely coupled system. So maybe from there, you can maybe show what was next afterwards.
Okay. Recap, huh? We do a recap. At that point, then we proceed Unfortunately, we didn't meet last week. Okay, so let me do that. Yeah, so Sylvia there? Sylvia?
Yes, there.
At that point,
yeah, there.
Okay, good. So we had just looked at the two extremes of a spectrum of a distributed operating system. And a distributed operating system operates within a DS, or a distributed system. So the tightly coupled systems and the loosely coupled systems. And we said that a perfect environment for a distributed system would be the tightly coupled system. But of course, if you use a tightly coupled system, then the operating system is one. Okay, but what now would make a distributed system better would be the loosely coupled system. Because if it's a loosely coupled system, then you now have every system running on its own operating system. So multiple operating systems used. Okay, in a distributed system, it is better to use multiple operating systems. And then now, when you have users having that kind of a freedom of using their own operating system, the better. And also, we can end up now creating a single global view. So even if people use their operating systems or their own platforms, then we should create a global view. So creating a global view makes the entire organization operate having a tightly coupled system. So the two extremes can then be used. Okay, we can use the two extremes. So using the two extremes now makes the distributed system better. Okay, it makes the distributed system better for use. So our next task then is to look at the transparencies. Okay, there are different forms of transparencies that may be used. Remember last time we said that when it comes to use of transparency choices, what now we want to do is to ensure that we hide the complexities of the system from the users. So hiding the complexities of the system from the users, but still ensuring that the users can be able to perform certain tasks. Now, let me just get to this slide number 18. Okay, slide number 19 there. Now, there are two wide choices, okay? There are two wide choices of transparencies that can be used in a distributed system. And these now include the distributed transparency from the perspective of ensuring that the users can be able to view certain features within that particular system, that they can be able to do certain things, okay? So they should be able to do certain things. And so we are not denying the users the access to certain resources that may be important to them, okay? So the two major choices include the full distribution, okay, and the partial distribution. When it comes to full distribution, what now happens is that all the complexities and all the features of the system are hidden from the users. Okay, so a user is not able to do anything. A user is not able to upgrade. A user is not able to even access certain features of that particular system that they may need. And so when it comes to full distribution is outdated these days. Okay, we're living in the age when you don't actually expect the users to entirely rely on the system admin or the network admin. Okay, a user should be able to do some of these tasks on their own. Okay, so we don't expect a user now to rely on the system admin all the time. Okay, for example, when it comes to running some of the diagnostics, the diagnostic tools, the user should be able to run them. The user should be able to update even the antivirus softwares. The user should be able to update some of the maintenance tools that they use on a daily basis. Okay, they should be able to update some maintenance tools on their own. So they don't necessarily have to rely on the support people all the time. Okay, you guys have gone out on attachment many times, and when you go out on attachment, you realize that some of these managers or some of these people who use their systems on a day-to-day basis. They call you all the time to perform tasks for them. They call you all the time to set up their systems for them, okay, which should not actually be the case. The users we have these days, they are literate, okay, and so when a user is literate, they should not be calling the support people all the time to perform some of the functions or some of the tasks for them. Okay, they should be able to perform those tasks for them, and therefore, the kind of transparency choice that is that's appropriate for users is partial or what we call selective distribution transparency. So if it is partial, then what you now do as a designer is to select the particular transparency features or forms of transparencies that are more appropriate to them, okay, that are more appropriate to them in the organization. So the partial or the selective distribution transparency now aims at giving users access to some particular forms of transparencies that would be appropriate to them or that would help them now perform tasks effectively within the organization. And that's why we are saying that the application designer needs to now think of which particular components are more appropriate to particular users in certain environments, depending on the specific needs that they have within the organization, okay, based on the tasks that they perform within the organization. So that is what we are talking about with regard to this. So partial or selective distribution transparency is more appropriate, but not full distribution transparency. These days, we can't use full distribution transparency within the organization. And therefore, that would depend on the particular choice or the particular type of transparency would depend on the tasks that the users perform within their organizations, okay? And so there are different types of transparencies. There are different types of transparencies that would therefore recommend for use within the organizations. One is access transparency. Okay, for access, what we are now saying is that you now decide on how the users are supposed to access the resources within the different parts of the organization. For example, looking at JQuat with the different campuses and JQuat with the different users, okay? So you can hide the use of communication, okay, to access remote resources like programs, files, or data, or printers to different users, okay? So a user accessing a resource in current campus should not actually be complaining that when you're in current campus, this is how to access the resource. But when you're in the CBD campus, this is how to access the resource, okay? So the way they access the resources should be the same across, okay? Because if you're a network admin and you find yourself in the CBD or in the Juja campus, you should be able to administer the resources the same way, okay, regardless of where you are within the organization. So the access should be the same across. So that's what we are saying there. So from a programmer's point of view, the access method to a remote object should actually be identical all over. Okay. Just a minute. Let me sort out. everyone can hear me now, and we may proceed with this. It's not displaying. Okay, Dennis, now you can see this.
Yes.
What can you see?
Types of transparencies.
Okay, good. So I've just mentioned something on access transparency, and people should be able to view resources the same way, okay, regardless of their locations. And so people should be able to access resources regardless of the same way, regardless of their physical locations. And therefore, hiding the complexities in terms of the location of the resource would be very important. So the designer of a DS should actually take note of that, such that now a user, as long as a user is virtually able to access the resource, they should be able to access it regardless of their physical locations. Then next, for us now to implement the access transparency, the syntactical structure of the distributed system is always very important to us. The syntactical structure of a DS should not be exposed to the users, because here we'd be looking at the logical access and also the physical access, okay? And of course now the concept behind the access to the resources should also be hidden from the users. So you keep the same semantics across, okay, in terms of the logical structure and also the physical structure. All that should be kept uniform across the distributed system. Now, in terms of location transparency, any details of the topology or any details of the physical structure of the system should be of no concern to the user. So a user accessing it in current campus should be able to access it without any interference on the location structure, okay, or without interference of the topological structure of the system. So even when it comes to naming, you name the resources without giving any details about the physical location of the resource, okay? So a name should not give a hint as to the location of that particular resource. You don't name resources using people's names, okay? For example, you are calling it Andrew's printer or Dennis printer, okay? That should not happen. Give names that do not give any hint on the physical location of the resource. Do not give any hint on the person using that particular resource. So that is very important to us. Then we've mentioned something on the location and also the access. That is very important to us. Then next, on concurrency transparency, always the designer should name the resources without, should actually design the resources without interfering with the number of people who may have access to that particular resource concurrently, okay? When I'm accessing the resource, the fact that I'm accessing it should not interfere with somebody else who is accessing the same resource concurrently. For example, if lecturers are to access the system, the grading system, and process the grades for their class, okay, you are accessing the grades, you're accessing the system and then processing the results for your class. The fact that I'm accessing the system and processing the results for my class, that should not hinder another lecturer the access to that particular system. Okay, so we should be able to access the system and process our results without interfering with each other. So that's where concurrency, transparency comes in. The fact that I'm accessing the resource does not hinder somebody else from accessing the same resource. Somebody else can access the same system and process their own results within that particular system. So that is what we are looking at with regard to concurrency transparency, because several users and several applications may be active at the same time, but without interfering with each other. So that is key. Then next, on replication transparency, always a designer should hide the differences between the replicated files. Resources may be replicated, and when they're replicated, I should not actually be given wrong data, or wrong data should not be available to me simply because that particular resource is replicated. The replication of resources should be real time, okay? Should be real time, such that if it is a student's transcript, for example, being accessed in current campus and then modified by someone in current campus, okay, the modification or the edited records should be replicated and be seen by the registrar in the Juja campus immediately for that particular student. Okay, so any change should be done real time. So files can be replicated, yes, but the fact that they are replicated should not actually make somebody access wrong data. Okay, so you hide the differences between the replicated and the non-replicated resources. Now, for migration transparency, if an object or a process or a resource happens to move from one location to another, then that movement should be hidden to the users. Okay, a resource can always migrate, a process can migrate from one location to another location. The fact that, let's say, a staff member has moved his access point from current campus to Juja campus, that information should not be given to the users. Users should not be able to access it. As long as you can access a resource virtually on the system, remotely, then that access is enough. Okay, so hide any differences between the different hosts for that particular resource from the users. Okay, so this particularly now means to us that resources can always be relocated. We can relocate resources dynamically without interfering with users' access, and also without reconfiguring the system, because reconfiguration is very important to us. Okay, but should only be done when very necessary. Okay, we cannot reconfigure our system simply because a user has moved from one location to another location. Then next, on performance transparency, any performance overheads should be hidden from the users. Okay, users should not be complaining that when you're in current campus, the system performs better than when you're in Juja campus. Okay, so users should not be able to tell any performance overheads that do exist within the system. Because if that is the case, then what would happen is that users would be going to a particular location in order for them to access good performance of that particular system. So performance should be uniform across. Okay, so resources must be located in particular areas where we know that the performance is uniform. Okay. Then when it comes to scaling, a system can always grow, but the growth of the system should not interfere with the performance of the system. Okay, the system should actually grow without affecting the application algorithms, without affecting the user access to the resources. That is very important to us. For example, many times we have seen companies like, let's say, Safaricom telling us that M-Pesa services will not be available between, let's say, 6 a.m. and 8 a.m. Okay, simply because we are doing upgrading of the M-Pesa server, which is wrong. That means in terms of scaling transparency, it is lacking something. Something needs to be done there. Okay, the fact that you are upgrading the system, that does not actually interfere with user access. Or even Kenya Power sends us messages saying that the prepaid tokens will not be available tomorrow. So if you want to buy prepaid tokens, buy them in advance. But how many Kenyans buy such resources in advance? Very few. Okay, many of us only buy such resources when we need them. Okay, you can't be accessing the M-Pesa services in advance. You access the M-Pesa service when you need it. Okay, so if it is prepaid tokens, you only buy when you need it. Okay, because very few Kenyans would actually buy prepaid tokens in stock. Okay, you buy a stock of prepaid tokens and then you keep it for future use. You only buy it probably when you find yourself in a blackout. That's when now you think of buying the prepaid tokens. Okay, and you buy in small quantities, or even air. Okay, those of you who use who buy airtime through the cards. Okay, so you buy it only when you need it. So you didn't actually buy a big stock that you don't need immediately. So scaling transparency is a major issue. The next is fault transparency. For fault transparency, the system should be able to hide software and hardware failures whenever they occur. And any software and hardware failures, when they occur, should not interfere with user access, should not interfere with the performance of the system. So that's what we are saying there. So a fault-tolerant system is a system that will be able to continue working even in the event of a tragedy or in the event of a failure. Okay, and then a fault-tolerant system would always start doing what we refer to as the troubleshooting process. Okay, so the troubleshooting would be a three-stage process that involves identifying the fault, locating the fault, and then getting rid of the fault or trying to get rid of the fault. So in a software system, we would expect that the system is fault transparent. Okay, so any fault does not interfere with the user access. Any fault should be hidden as much as possible, and then there should be a fault reporting mechanism. Okay, so a fault reporting mechanism where now the system reports the failure to the admin. So that's all right. Now next is the issues in design of a DS. Okay, the major issues that any developer of a DS should always consider. One is transparency, which we already talked about, fault tolerance, openness, concurrency, scalability, and performance. So a few things about transparency again. Of course, we have already talked a lot about transparency, but we can say something more about it with regard to the design of a distributed system. And we've already said that transparency involves hiding the complexities of the system from the users and also giving the user only what the user requires. Okay, so you give the user the access to only what they require. So the concealment, okay, of some of those functionalities from the users and the application programmers, okay, you conceal some of the important functionalities that you do not want the user to see or that you do not want the user to detect. Okay, we have talked about performance transparency. You don't want the users to be able to tell that when you're in current campus, the system performs better than when you're in junior campus. Okay, because people would always tend to flock around the area where the system performs better. So some of those failures or some of those transparency issues could be with regard to the users, okay? How the user issues the commands, how the user gives instructions to the system. So that's okay. Then number two is fault tolerance, which I've already talked about. The ability of the system now to continue working, okay, even in the event of a failure, okay, because a fault-tolerant system is always necessary in every organization. And a fault-tolerant system is always reliable, okay? It is reliable simply because of the fact that it can manage the faults, okay? And therefore, whatever kind of hardware or software that we're using would not break down. So that is key. So when we implement the fault tolerance features, we end up now reducing the cost of maintenance. Okay, the system cost would be so much reduced because you wouldn't lose the hardware, you didn't lose the software as well. Okay, But of course, recovery mechanisms would be important to us. We develop, and then we maintain, then we test. Okay, when there is any troubleshooting to be done, then now we have to locate the faults, and then we try to eliminate those particular faults. So that is important to us. Number 3 is concurrency. Concurrency is where now several users and several applications are considered to be active, and so they are running in parallel. Okay, and so if these processes are to run in parallel, they must be controlled. Okay, they must be controlled, and there has to be some level of consistency. Okay, we'd expect some level of consistency within the system. Okay, and of course now when systems are concurrent within the organization, there's always a tendency of having certain problems. There are those problems that arise when we allow concurrency of the tasks, concurrency of the applications, and also of the users' tasks that are running on the system. And so what I would want you to do is this. I'll give you a question, some task on the problems that arise from concurrency issues. Okay, you must have talked about concurrency in database systems with regard to atomic transactions, all those. Okay, some of the problems that arise from concurrency within a database system. Okay, they include loss update, dirty read, non-repeatable read, phantom record. What you need to do there is to pick an example of a business transaction. You pick an example of a business transaction, and then now you explain what now happens in the case of loss update, dirty read, non-repeatable read, and phantom record. So I'll give you a question on that later. Okay. Then scalability, we've already talked about scalability. Okay. A scalable system is a system that allows growth. So it allows growth within the system. So the system continues to grow without interfering with service delivery. So that is a scalable system. So scalability is key because we always expect the organization to grow. We also expect the system to grow. Okay. And therefore the system only grows when the system only grows without disruption of service when the system is scalable enough. So scalability is therefore a requirement, which is very important to us. You minimize any overheads when it comes to the access to the resources. So that is key. And then finally here is performance. Okay. You see now you're looking at the performance of the system, and there has to be a performance measure. The performance measure could be the output that we are getting out of the system. It could be the accuracy with which the system works, okay? And also it could be with regard to efficiency of the system. Because when it is efficiency of the system, all that you are looking at is whether the system can generate certain output within a given time. Okay, and so what is the level of the efficiency of that particular system? Okay, a highly efficient system would actually minimize waste of resources. Okay, for example, if it consumes a lot of power, then it means that particular system is not very productive. Okay, because you're looking at the performance measure, and performance measure is a measure that we use or a criteria that we use in determining how successful the system is. So the two main parameters here include the response time and the throughput. The response time is simply the average elapsed time, the time that the system requires in order for it now to generate certain output. Okay, so the average time that elapses, okay, from the time or from the moment the user is ready to transmit and the entire response is received. So the time that you've taken processing, okay, that must be considered. The time that you've taken even when fetching for certain input, okay, that must also be considered as part of the response time because it is the average elapsed time from the moment the user is ready to transmit and the entire response is received. The entire response is simply the output that we get out of the system when we issue certain commands. Then number 2 is the throughput. The throughput is the number of requests that would be handled per unit time by the system. Okay, what's the number of requests? So the average number of requests that we can be able to execute. That now becomes its throughput. And of course, now for any kind of a system, we'd always want to increase the throughput as much as possible. So that is the end of our chapter. That's the end of our chapter. So now we can go to chapter 2. Are you with me? Are you still with me?
Yes.
Anyone with
Yes,
me?
Malim.
Oh, yes,
Yeah,
Mwangi, Dennis.
yes.
Yes, Dennis, correct. Good.
Yes.
Okay. Esther. I can see Esther there. Esther, are you there? Esther?
Yes, I am here.
Oh, you joined late, huh? You
By a
joined
few
late.
minutes.
Huh?
A few minutes.
Okay, so, all right. So now we move to item number 2. We go through this very fast. This is where we were supposed to start today. It's only that we missed it last week. We missed our class last week, so we were supposed to start from here in our class. Just a minute. Can you see anything, Esther? Can you see my
Pardon?
screen? Can you see my screen?
Yes, I can.
What can you see?
Middleware.
Oh, okay. So the middleware layer is that layer of software that exists between a client process and a server process. I know some of you are doing a unit known as, or you've done a unit known as systems programming. Okay. And in that unit, that's where you talk a lot about client and server processes. In a distributed system environment, you'd have the server. The server receives the request and then services those requests. A client process sends a request to the server process. And so when it sends a request to the server process processes the request and then returns the result to the client process. Okay. And normally, even when you log in from your access point or from your machine, when you're logging in, you're simply sending a request to the server. So you are initiating a client process, and this client process now communicates to the server process. Then the server process will do the authentication for you and then confirms whether you're one of the authorized users. And then after that, now you are given the access. Okay. Now the layers, this layer therefore performs a number of tasks between the client and the server processes. Okay. And then also the middleware layer is that layer of software that exists between an application software and the operating system software. Okay. And its main role is simply now to shield the system or even the client from the complexity of the underlying features, okay, of the platform. So the client or the user application is shielded from the complexity of the server process, okay? If it's an application software, the user who is now accessing the system through the application software is shielded from the complexity of the underlying operating system platform features, okay? So that is very important to us. And this is now the main role of having the middleware layer. Okay. So what is important to us next would be the services that would expect the middleware layer to offer to us. Okay. That's what we are going to look at after this. And here now, the next thing is what middleware models are used. What kind of models are used? There are usually two main models that are used in implementing the middleware layer. Okay, and the first one is where now the system treats everything as a file. So all the components are treated as a file within the system, and this mainly with Unix operating system, where all the I/O devices are treated as files. Okay, the printers, the input devices, all the output devices, they would all be treated as files. And so within the operating system, there is a file that identifies the printer, or there is a routine, okay, or there's a code for that particular printer, written for the printer, in order for us now to be able to access the printer. So every time you load in or you install a new device, okay, then the operating system must now set up a code that would identify that particular device. Okay, so that would always be very important to us. Some kind of a routine is set aside for that particular device, for accessing the device. Okay, and that's why normally even the device drivers would become part of the operating system. So through the device driver, we can be able to communicate to the device that is out there. Okay, and then the other important one is the remote procedure call, RPC, what we call RPC. For RPC, it is a typical environment where we'd have the communication between a client process and a server process. So the client process builds up the message and then sends it to the server process. When the server process receives it, the server process now decides on whether to attend to this particular service or not. Or it now decides on the kind of output to give out or the response to give out to the client process. Okay. But of course, all that is important is hiding the network communication. Okay. We hide the network communication, we create a barrier or we create a layer. So the communication, only some little communication will go through that particular barrier. So that's where the middleware layer lies. Okay. Okay, just a minute. So the distributed objects are the key objects that are behind the use of the middleware layer. Okay, so the distributed objects will pass through the middleware layer. Okay, so it's also okay. But of course, all the data or all the information would be kept in the form of documents. Okay, and each one of them now resides at a machine that is transparently located somewhere in the world. We can decide to now distribute it elsewhere in the world. So that's okay. Such that now, if it's a document, then every document must have a link. For example, if it's on the web, every document must have a link, and through the link, now we can be able to refer to that document. So that is key as well. Now, on the middleware services, there are a number of middleware services that are offered, services that the middleware layer offers to us. We can categorize them in different ways. We can categorize them first in terms of the communication services, the naming services, the distributed transaction services, the security services, okay, that the middleware layer performs. So now, the detailed services could be name to address resolution, which is now a communication service, dynamic server process invocation, and then locating particular servers, how to locate the servers within the entire organization. Then load balancing. Load balancing simply means that a particular server should not be overloaded with 10 requests or several requests, yet there's another server somewhere with the same capability which can execute those particular tasks. So some of those tasks should be transferred to another server or to another server process. Okay, so one particular server should not be loaded with all the requests, yet some of those requests can be transferred to another or a different server somewhere within the organization. So load balancing is very important to us: security, failure recovery, message routing. That now involves determining the actual route or the particular route that particular agent is supposed to follow. So that is key, okay? And then reliable message delivery, okay? Reliable message delivery with regard to communication, which is key. Now, just to say a few things about communication services. Communication services involves message routing, okay? Ensuring that messages are routed appropriately, and they're routed along the paths that they're supposed to follow, okay? So communication facilities must be provided. Communication services must be provided. How do we communicate to people, and where do we communicate, and at what time do we communicate? Okay, there could be traffic jam somewhere, and so sometimes even communication becomes difficult. Okay, you wonder, how are you going to pass the information, or how are you going to communicate? But what would always be important is define the route that you're supposed to follow at any given time when you set out to pass the information, whether it's logically or virtually, or it is physically. Okay, so communication services, that is a major service that the middleware layer offers to the user. So it determines what kind of requests are to pass through, okay, to the server process. So that's okay. On naming services, we said earlier on that there has to be naming transparency, okay? And what happens there is that give names that will not require reconfiguration, okay? When the system now develops, or when the system now grows up, or the system now expands, okay? And at this point now, scalability should not be a problem, but should be taken into account. So that is key as well. And so naming services is key. For example, now when it comes to the web, on the web, when you happen to relocate a resource on the web, then what now happens is that the URL of that particular resource will have changed, okay? So you don't just move a resource without thinking about its URL. The URL must be somewhere, so it is rooted somewhere. It has roots that go back to a particular location. Okay, so naming services is key there. I hope you're still with me. Are you with me? Dennis?
Yes.
You are,
Yes.
huh? Okay. All right. Then next is distributed transaction services. The transaction services are distributed simply because of the nature of the distributed system. Okay, so when you're in a particular environment, the facilities that would enable you to be to distribute transactions would be key, because a distributed system without transaction services is not useful to us, and the transaction services that it offers must be distributed. Okay, that must be distributed. How you access certain resources and what you do with them, okay, distribution will always be very necessary in order for us now to keep information about you, okay, or about the service or a resource. So that is key. So distributed transaction services, that is important to us. Then security services. Security is a major challenge in distributed systems, and we said that, okay, simply because of the multiple access points, okay. So the middleware layer defines the kind of security measure, or the level of security measure that is to be implemented within the organization. The system may be so secure simply because of the middleware layer that exists. Okay, and so the middleware layer must actually understand. Okay, must actually understand the kind of people we are dealing with. Okay, so whoever manages the middleware layer must understand that. Okay, so that is key. But of course, security is always a major challenge in distributed systems. So that's something that you should be able to find out and even discuss. Okay. Now, in terms of the middleware layer and openness, the middleware and openness, from what I've just said, security is a major challenge. And so the issue of security must be addressed first before we think of the middleware and openness. Okay? Because when we construct middleware layer, okay, we are constructing it for a range of operating systems. So you may have a middleware layer running on some Windows operating system or several Windows operating systems, but it still runs on a different operating system. Okay, and it can be used there. So the level of independence is therefore very, very key. Okay, but we tend to depend so much on the hardware that's available. You are depending so much on the hardware that is available, and then you end up forgetting many things about the software that is that can be used. Okay, the kind of software that can be used. So now, this is the last item in this chapter, the middleware and openness. A good system should be as open as possible, so that is important to us, even though it brings its own challenges, okay? But the middleware layer should provide access to the server resources, okay? Or even the server process itself. So that is key there. Now, our next chapter now will be chapter 3. That will be chapter 3, and I think this chapter we can look at it next week. Chapter 3, message passing. So message passing is our next chapter. So Dennis, we've looked at chapter 1, introduction. We've looked at the middleware today, and then now next week, message passing. Sawa. Is that okay, Deborah?
It's okay.
Yes, it's okay.
Yes.
So next week we are doing physical, all right?
Okay.
Okay, Dennis?
Yes.
Yes. Esther, confirm?
Yes.
Yes, so we do physical next week at 11. So let's keep time on Thursday next week. So that's all right. Have a good day, guys.
Okay.